In the last videos, we talked about reachability and availability. Those concepts often sound binary. Either an endpoint is reachable or it isn't. Either it's available or it's not. But real networks rarely fail in such clean ways. Today, we're talking about something far more common and far more dangerous. Endpoint partial failure. Endpoint partial failure describes a situation where an endpoint is not completely broken, but not fully functional either. It still exists. It still responds sometimes. But something inside it is no longer behaving correctly. A useful metaphor is a malfunctioning elevator. The elevator still has power. The doors still open. But sometimes it stops between floors or ignores button presses. From the outside, the building looks fine, but using the elevator becomes unpredictable. That's what partial failure looks like in networking. At a basic level, an endpoint experiencing partial failure may still be reachable. Packets can reach it. Connections may still be established, but once communication begins, something goes wrong. Responses may be slow. Requests may fail intermittently. Only certain operations may work. This is what makes partial failures so difficult. Complete failures are obvious. Partial failures are deceptive. From the network's perspective, the endpoint appears alive. Health checks may pass. Basic probes may succeed. But real traffic experiences problems. One common form of partial failure involves performance degradation. An endpoint may respond, but far too slowly. It accepts connections, but cannot process requests fast enough. From the client's point of view, the endpoint exists, but it feels broken. Another form involves functional failure. Some parts of the endpoint work, others do not. A server may serve static content correctly, but fail on dynamic requests. An endpoint may authenticate users successfully, but fail when accessing downstream services. In these cases, the endpoint is neither fully healthy nor fully failed. It occupies an unstable middle state. Partial failure often originates from resource exhaustion, CPU saturation, memory pressure, thread pool exhaustion, disk or network bottlenecks. The endpoint is still running, but it is operating beyond its safe limits. This is like a shop that is open but overwhelmed. Customers can enter, but service is slow, inconsistent, and error-prone. Dependency failure is another major cause. An endpoint may rely on other endpoints to function. If one dependency becomes slow or unreliable, the endpoint itself may enter partial failure. It is still running, but it cannot complete its work correctly. This creates cascading effects. One partial failure spreads to others, even though no single endpoint is completely down. From a network behavior standpoint, partial failures are extremely disruptive. Traffic is not cleanly rerouted because the endpoint still appears reachable. Load balancers may continue sending traffic, assuming the endpoint is healthy. Retries increase. Timeouts accumulate. Latency spikes. The network becomes noisy and inefficient. Partial failures also confuse monitoring systems. Simple up or down checks often miss them. The endpoint responds, so it appears healthy. But users experience errors. This mismatch between observed health and actual behavior is a hallmark of partial failure. This is why modern systems rely on deeper signals. Response times, error rates, success ratios, application-level health checks. The goal is not just to detect whether an endpoint is alive, but whether it is functioning correctly. Partial failure also affects trust. An endpoint that behaves inconsistently becomes unreliable. Networks may gradually reduce traffic to it instead of cutting it off entirely. This behavior is similar to how people lose trust. One mistake is tolerated. Repeated inconsistencies change expectations. In distributed systems, partial failure is considered the normal failure mode. Systems are designed with the assumption that components will degrade before they fail completely. Endpoints may slow down before crashing. Dependencies may time out before disconnecting. Network behavior must adapt to these gray zones. This is why techniques like circuit breakers exist. When an endpoint begins to fail partially, traffic is reduced or stopped proactively. The system protects itself by treating partial failure as a signal, not an anomaly. Endpoint partial failure also shapes retry behavior. Retries are helpful when failures are brief and complete. But during partial failure, retries often make things worse. They add more load to an already struggling endpoint. This can push the endpoint from partial failure into total failure. Understanding partial failure helps explain why careless retries can destabilize networks. From a design perspective, endpoint partial failure is not something to eliminate completely. It is something to manage. You cannot prevent every slowdown or dependency issue. But you can design networks that tolerate degradation gracefully. Traffic can be shifted, endpoints can be isolated, failures can be contained. Understanding endpoint partial failure changes how you interpret network problems. Instead of asking whether an endpoint is up or down, you ask how well it is functioning. Instead of assuming binary states, you look for trends and degradation. Endpoint partial failure is the space between healthy and broken. And in real networks, that space is where most problems live. That is endpoint partial failure.